Hello and welcome to my lecture on mathematical modeling of dynamic systems from first principles in the subject state space approach to control system analysis and design. In the last lecture, I introduced to you the concept of state space and the standard state space representation of dynamical systems. Now, in this lecture and in subsequent few lectures, we will understand with the help of a few examples mathematical modeling of physical systems based on the first principles and expressing the model equations into standard state space form. What I am trying to say is that we will write the governing equations of the given physical systems. Generally, the governing equations so obtained will not be directly usable by the control engineer. In the state space approach in particular, we want the model equation in the state space form. So, the governing equations are to be put in the standard state space form. Governing equations are obtained on the basis of first principles, which means laws such as Kirchhoff's current law or Kirchhoff's voltage law or thermodynamic principles or equations of motions or equations of chemical kinetics, principles of mass balance, heat balance, etc. So these are the first principles, and based on that we work out the mathematical models. So we call them mathematical modeling based on the first principles. That is different from the empirical methods of mathematical modeling, which is altogether a different topic in systems identification. Specifically in this lecture, we will write the equations governing the given physical system and thereafter express them into the form this x dot equal to ax plus bu and y equal to cx plus du. This one is called as the state equation, as I told in my earlier lecture, and this is called as the output equation. And we will give the values of A, B, C and D matrices in each case. We move to the first example, which is an operational amplifier circuit, and it is shown here. It is very simple. You can see that an input voltage Vi is applied to a series interconnection of resistance R1 and capacitance C1, such that the current in this branch is I1, which is indicated here, you can see, and corresponding electric charge is Q1. The feedback branch consists of a parallel interconnection of this resistance R2 and this capacitance C2. The respective branch currents are I2 and the charge is Q2. The current in capacitance is I3 and the charge is Q3. So we are going to develop the mathematical equations and express them into the standard form. First, what we do, we apply the Kirchhoff's voltage law in this branch. So you can see the voltage Vi is causing a current I1 in this series branch, and this is at zero potential. So this Vi will be the drop across the resistance R1 and the drop across the resistance C1. And this is the equation showing this. Vi is R1 I1 plus 1 by C1 integral of I1 dt. Now what we can do is, we can divide both the sides of this equation by R1, and simultaneously we can make a substitution, because this I1 dt integral of this is equal to Q1, the charge. So division throughout by R1 and substituting integral I1 dt by Q1 and I1 by dQ1 by dt, we can express this equation into this form. dQ1 by dt will be equal to minus 1 by R1 C1 Q1. This, when we divide by R1, it becomes 1 by R1 C1, and this integral I1 dt will be equal to Q1. So this becomes Q1 1 by R1 C1, and this Vi gets also divided by R1. So we have 1 by R1 here dividing Vi. So we get the first differential equation describing the circuit, which is dQ1 by dt is equal to minus 1 by R1 C1 Q1 plus 1 by R1 VIT. Next, we consider the feedback loop, this one, and what we notice that, excuse me for a moment, what we notice that this R2 is in parallel to C2. That means the voltage drop across R2 will be exactly equal to voltage drop across C2. That is one. Second thing, we see that these currents I2, I3 and I1, all these three currents enter the same junction. So sum of the three currents should be equal to 0. That will be obtained if we apply the KCL. So with these things in mind, we see that we will have this equation first. The voltage drops across the resistance R2 and the capacitance C2 must equal each other. So we get I2 R2 equal to 1 by C2 integral I3 dt. And KCL applied at that junction at the inverting input of the operational amplifier gives I1 plus I2 plus I3 equal to 0, or I3 can be expressed in terms of I1 and I2 like this. And because I3, its integral is the charge Q3, so we can also write Q3 equal to minus of Q1 minus of Q2. So we will substitute in place of integral I3 dt, we will substitute Q3, and that Q3 will be sum of Q1 and Q2 with a minus sign. So we will have minus Q1 minus Q2. So this equation gives I2 into R2 equal to 1 by C2 bracket minus Q1 minus Q2. And if we divide throughout by R2 and simultaneously in place of I2 we substitute dQ2 by dt, we will have R2 dQ2 by dt equal to minus 1 by C2 Q3, or dQ2 by dt, this thing will be equal to this thing, where Q3 has been substituted in terms of Q1 and Q2. So dividing by R2 will convert that equation into this form. So this is another differential equation. I have brought the picture of operational amplifier circuit here again. We see that output voltage VO is the voltage across the capacitor. It is of course also the voltage across the resistor, but let us consider first that it is equal to the voltage across the capacitor. So VO can be written like this, 1 by C2 integral of I3 dt, or because this integral I3 dt is same as Q3, so it becomes 1 by C2 into Q3. And remember that this Q3 was expressed in terms of Q1 and Q2. So this output voltage gets expressed in terms of Q1 and Q2 by this relation. VO equal to minus 1 by C1 Q1 minus 1 by C2 Q2. So we obtained the equations describing this circuit. One equation was here, dQ1 by dt, this equation, dq1 by dt equal to minus 1 by r1 c1 q1 plus 1 by r1 vi. Other the equation is here dqt by dt equal to minus 1 by r2 c2 q1 minus 1 by r2 c2 q2, and the output equation is here va equal to minus 1 by c2 q1 minus 1 by c2 q2. Once we got the equation, now the next job is to convert them into the standard state space form. So we have to identify the state variables, which are now identified like this. The charge q1 we identify as the state x1. Charge q2 we identify as the state x2. So we have the state vector xt equal to x1, x2, which is q1 and q2. The input is of course the applied voltage Vi, you can see, and the output is the output voltage of the operational amplifier, which is Vo. So, as we can notice from one of the differential equations which we wrote here, this equation, dq1 by dt, now q1 has been obtained identified as x1. So this is dx1 by dt equal to minus 1 by r1 c1 into x1 plus 1 by r1 into vi, the applied voltage. The other equation, because q2 has been expressed as x2, has been identified as the second state x2, so this can be rewritten as dx2 by dt equal to minus 1 by r2 c2 q1 minus 1 by r2 c2 q2. And when these are written in the matrix form, then we have this, that x1 dot equal to minus 1 by c1, 1 by r1 c1 x1, so that gives the element a11 as minus 1 by r1 c1. x1 did not contain a term of x2, so we have here 0, this term. Second differential equation, x2 dot was minus 1 by r2 c2 into x1, so we have this coefficient as minus 1 by r2 c2. It also contained another term of x2 through this multiplier, so we have minus 1 by r2 c2 as this element in this place. The input was one entering in the first equation, minus 1 by r1 into vi. You can see it was here, this vi was coming through 1 by r1, so that reflects here as 1 by r1 into u. And in the second equation, you can see in the previous slide it was there is no vi term, so we have a 0 coefficient there. This v2 coefficient is 0 into u. And the output is the output voltage Vo, which is written as minus 1 by C2, here it comes from here, minus 1 by C2 into Q1, which is X1, minus 1 by C2 into Q2, which is X2. So this equation gives minus 1 by C2, minus 1 by C2, the two coefficients in the matrix C into XT. So this gives the mathematical model of the operational amplifier circuit. What I want to do is, as an exercise, the same equation, same circuit, what you do is that please consider Q1 and Q3 as the state variables instead of Q1 and Q2, which was done, and obtain the state and output equations. Now let us go to the second example, which is that of an electromagnetic actuator. It is shown schematically in this figure. There is an electrical solenoid in which we have the core. Its core is of mass m1, it is shown here. A voltage E is applied to the solenoid, and the solenoid has resistance R and the inductance L. This mass is coupled on one side to the lever or here, and on the other side it is connected to a fixed point through a spring with the stiffness K1 and dash part with damping coefficient beta 1, which is written here. The lever arm is coupled on the other side of the support to mass M2, and it is also connected through a spring with the stiffness K2 and dash part with damping coefficient B2 to a fixed reference as shown here. We have to obtain the mathematical equation. Of course, the electric current which flows in this solenoid is assumed to produce a force Ft on the mass M1, which is proportional to the electric current. Ft is mu times It. And the direction Z1, which is shown here, down, is assumed as the positive direction. Also see that because this lever is supported somewhere in the center, so we have Z1 and Z2, they will be related to each other. Downward motion Z1 is result into upward motion Z2 of mass M2. So with this, let us move to model this electromagnetic actuator. So if we apply the force balance on mass M1, this one, then we'll see that the components of forces are its own force due to inertia, which is M1 into d2z1 by dt square. This is expressing the acceleration, plus beta 1 into dz1 by dt is the force due to this dash part, and k1z1 is the force due to the spring. So these forces are in this direction, that inertia force of mass also, and there is a force because motion of the lever this side results into motion of the lever on this side pulling the mass M2 against the spring force K2 and the dash part force through beta 2 and the force of inertia of mass M2. So that force is F2. So we have M1 d2z1 by dt square plus beta 1 dz1 by dt plus k1z1 plus F2 all balancing to the force Ft due to the current in the coil, which is mu times It. Similarly, if we consider the force balance on this part consisting of the mass, the spring K2 and the dash part B2, then we will have M2 d2z2 by dt square plus beta 2 dz2 by dt plus K2z2 balancing to F2. Now here we will invoke the relation that Z1 by D1 will be equal to Z2 by D2. So what we can do is, in this second equation, we can substitute Z2 equal to D2 by D1 into Z1. And so the second equation converts like this: M2 into D2 by D1 into D2 Z1 by dt square. This is the expression for D2 Z2 by dt square. This is for dz2 by dt in terms of Z1, and this is for Z2 in terms of Z1. So when we do this substitution, we obtain this equation shown here, and that means that Ft can be substituted in terms of F2 can be substituted in terms of these variables in the first equation here. In this equation, F2 can be substituted from there. So we obtain M equivalent d2z1 by dt square plus beta equivalent dz1 by dt plus k equivalent z1 equal to mu into I. And this M equivalent is combination of M1 and M2 like this. M equivalent is M1 plus M2 d2 by d1. Beta equivalent is beta 1 plus beta 2 d2 by d1. And K equivalent is K1 plus K2 d2 by d1. So we obtain one equation consisting of that system of masses M1 and M2 like this. The springs K1 and K2, they got assembled into K equivalent. The dashpots beta 1 and beta 2, they got converted into equivalent beta equivalent, and masses M1 and M2 got converted to M equivalent. Essentially it happened because the motion of this lever arm is restricted. Z1 and Z2 cannot be independent. They are dependent on each other. That is how it happened. So this is one differential equation. The second differential equation is obtained by considering the electric coil, this one, which is excited by the EMF E. It carries a current I and its resistance and inductance are respectively R and L. So it gives rise to L di by dt plus Rit equal to Et. This is by Kirchhoff's voltage law. So we have this differential equation governing that electrical coil. Okay, now we got the equations and now we have to identify the state variables. So what we do is we identify from this equation the position Z1, the position of the lever arm on the left on the mass M1 side, Z1 as one state variable and dz1 by dt, that is the velocity, as the other state variables. So we have x1 equal to z1 and x2 as velocity, that is z1 dot. Now we know that z1 dot is the derivative of z1. So we have x1 dot equal to x2. That gives this equation. And this d2z1 by dt square, this is equal to d dt of dz1 by dt, or d dt of z1 dot, and z1 dot has been identified as the state x2. So m equivalent x2 dot plus beta equivalent x2 plus k equivalent x1 will be equal to mu into I we have identified as the x3. So this equation gives x2 dot equal to k by m, k equivalent by m equivalent x1 minus beta equivalent by m equivalent x2 plus mu by m equivalent x3. This x3 is the current, x2 is the velocity of the lever on the left side, and x1 is the position of the lever on the left side, this way. So we get these two equations. Both these come from this differential equation, this one. And this x3 dot, the current in the coil, its derivative is given in terms of this x3 variable only and the input Et. So x3 dot is minus r by l x3 plus 1 by l Et. This is straightforward from this expression, dividing by l and substituting x3 in place of I. So dx3 by dt plus r by l it equal to 1 by l et, and change of side gives rise to this equation. So we have these three equations making the state equations. And the output we are interested is the position Z1, this position. So y is simply x1. Now we obtain the differential equations governing the circuit, and now we have to only put them in the state space form. That is done here. X dot, because x1 dot is x2, so we have x1 dot equal to 0x1 plus 1x2 plus 0x3. We have x2 dot equal to one coefficient into x1, another coefficient into x2, another coefficient into x3. So these three coefficients are one by one put here. This into x1, this into x2, this into x3. And again we didn't contain any input term, so we have 0 here, like that in the first equation. The third equation was x3 dot equal to minus r by l x3. So that means 0 times x1, 0 times x2 and minus r by l x3. So that is why minus r by l comes here. And through 1 by l it multiplied to the applied voltage ET, which is U, identified as the input. So we have this equation, this state equation governing the system, and the output equation, of course the output we identified was the moment of lever on the left side, which is Z1, so that gives y equal to 100x. So this gives the model of the electromagnetic actuator. I have exercise for you. So now instead of Z1, instead of Z1 as the state variable and Z1 dot, choose Z2 and Z2 dot as the state variables and Z1 as the output, and obtain the mathematical equations and thereafter the state space representation of the EM actuator. We move to our next example, which is a modeling of liquid level variations in an open tank. It is shown schematically here. We have a tank of uniform cross-sectional area. In that we have inflow coming as Qi and outflow going from it is Qo, and the instantaneous level is Ht. We have to model the liquid level variations into this tank. That is the problem. So this is of course much simpler system, simpler than the two systems which we considered before. And what we see is that this volume accumulated into this tank here, this volume given as Vt is area of cross section into the level in the tank, A times Ht. Now if we differentiate this, because A is constant, it doesn't vary with time, the differentiation will give dVt by dt equal to A dH by dt. And what we at the same time recognize that the accumulation of liquid is due to imbalance between Qi and Qo. If Qi is larger than Qo, the volume will increase with time. If Qi is smaller than Qo, the volume will decrease with time. So dVt by dt will be equal to Qi minus Qo. In other words, A dH by dt is equal to Qi minus Qo. We divide throughout by A, so we obtain this expression which gives dH by dt equal to Qi minus Qo divided by area of cross section A. This is the differential equation governing the liquid level variation with time in the tank. Now we recognize by applying the principles of hydraulics that through an opening in the tank, the outflow will be dependent on the square root of the liquid column. So QO is proportional to mu into root of H, this expression, and mu will of course depend upon the area of this opening and also its geometry. So the QO in a simple way can be written as mu times root of H. So we make this substitution in this expression to obtain dHT by dt equal to Qi minus mu root H divided by area of cross section A, or dH by dt equal to this one we bring here, so mu root ht by A plus this one we bring here Qi by A. So this is the differential equation governing the system, governing the level variation, and this is the output equation governing the outflow. So in fact we have obtained the governing equations for this circuit. Only we have to express these equations into the standard state space form, and because generally control system engineer is more comfortable with linearized model, we will first linearize the given equations. So what we do is we recognize that the equilibrium of the system is defined by the condition in which the inflow equals the outflow, and when they two are equal, the level also will be constant, which will be equal to H bar. So Qi bar, the equilibrium inflow, will be equal to Qo bar, the equilibrium outflow, which will be equal to mu into root H bar, mu times the square root of equilibrium water level in the tank. Now we consider incremental variations around this. So we consider Ht equal to H bar plus delta Ht, Qi equal to Qi bar, which is also Qo bar plus delta Qit, and Qo equal to Qo bar plus delta Qot. So first we express the output equation. The output equation was Qo equal to mu root H. So in this we make the substitution Qo equal to Qo bar plus delta Qo and H equal to H bar plus delta H. So we obtain Qo equal to Qo bar plus delta Qo, which is equal to mu root of H bar plus delta H. And simple mathematics, H bar plus delta H can be expressed as H bar common, this way H bar common, 1 plus delta H by H bar power half, this is also power half, and then this can be expressed as delta H by 2H bar, and a little manipulation will give this equation. Delta Qo will be equal to mu by 2 root H bar delta H. So we obtain linear equation corresponding to the outflow. Now let us obtain the linear equation corresponding to the liquid level. So what we do is we substitute in place of Qi here, in place of Qi, let us substitute Qi bar plus delta Qi here, and in place of Qo, Qo bar plus delta Qo, and in place of H, H bar plus delta H. So in that case, we will obtain this dH bar plus delta HT, this d of derivative of whole thing divided by dt, equal to this Qi bar was there, so that is equal to Qi bar plus delta Qi, and because Qi bar is equal to Qo bar, so we make this substitution, Qi bar equal to Qo bar plus delta Qi, and we have split the terms. Similarly, Qo bar is Qo bar plus delta Qo, so that Qi minus Qo becomes equal to Qo bar by Qo bar plus delta Qi minus Qo bar plus delta Qo, and with a minus sign, if we split, we get this one. And in that, these two terms cancel each other. So what we get, d delta h by dt equal to, what we have done, we have this delta Qo we have substituted in terms of delta H, which we obtained here. Delta Qo was obtained as this one. So this we have substituted in place of delta Qo to get it here. And delta Qi by A is here. We are keeping it intact. So we get d delta H by dt equal to, we get minus mu by 2a root h bar delta ht, which was obtained by substituting this delta Qo, and this delta Qi term gives this one. So this is the differential equation governing the incremental level change in the tank around the point of equilibrium. Now what we do is, at this point, we identify delta H itself as the state X of the system. So this equation will give us this state equation. X dot equal to minus mu by 2a root h straight away, and delta H is xt, so this one, plus 1 by a, delta Qi is the input. The incremental change in the input around the point of equilibrium we are expressing as the input u. And the output, which is delta Qo, we obtained in one of the previous slides. It is here. Delta Qo is mu by 2 root h bar into delta H. So that gives output y is mu by 2 root h bar x. So this system, the liquid level in the open tank, gets expressed by this state equation and this output equation. Of course, the system matrix is just consisting of one variable. It is just 1 by 1 matrix. The input matrix also is just 1 by 1 matrix, and the output matrix is also 1 by 1 matrix. So this system is a first order, however it was non-linear, and we linearized is to obtain A, B and C, all the three matrices as 1 by 1 matrices are just scalars, consisting 3 scalars. Now again, for this example, I have a suggestion for exercise for you. What you can do is, you can assume that this tank cross-sectional area varies with height. So A is some constant A0 plus beta times H. So, and thereafter you can go back to the first slide here. Now this A is dependent on height. So this A you will write as A0 plus beta H. And you will repeat the whole thing which was done in this slide, the next slide here, and the next slide here, to obtain the mathematical equation of the liquid level system in this case, where A is varying with height. The area of cross section is varying with the height. And thereafter, please obtain the standard state space form. That completes our third example. Now we consider the next example, which is of a numerically operated control valve. So these control valves They are used for automatic control of flow in the pipelines. Of course, we have manually operated control valves or automatic control valves. In the automatic, we have electrically operated or pneumatically operated. So we are considering the pneumatically operated control valve in a pipeline. So what is shown here is the schematic of a control valve. It has a diaphragm which is shown here, and on the diaphragm a control pressure P, small p, is applied. The area of diaphragm into this pressure results into the force on the diaphragm, let us say in this case upward side. This force is against the spring force, and also to that diaphragm attached is this valve stem, and to the valve stem attached is this valve plug, and this is the valve seat. So this application of air pressure on the diaphragm results into movement of stem up and down. So we have taken upward movement as positive. This movement of stem up and down results into change in area of this valve port, and because of that change in area, the flow through the valve changes. This flow changes. Of course, the upstream pressure is constant at P1, downstream pressure is constant at P2. So now we have to model the flow variations through this valve depending upon the applied air pressure P, the control signal. So various variables are listed here. A is the area of the diaphragm, M is the mass of the stem, the plug, all the moving parts attached to the diaphragm. Z is the valve position, P is the applied signal, K is the spring constant, P1 and P2 are respectively the upstream and downstream pressures in the pipeline. Beta represents the viscous frictional coefficient of the gland, and Q is the flow taking place through the valve. So we consider its mathematical modeling, which is fairly simple. Basically, as I was explaining, this air pressure in this side of the diaphragm results into a force on the diaphragm, and that force will result into the motion of the stem. So the three forces other than that control force, which is P times A represented here, are: one is the force of inertia. If the valve position is Z, then dz by dt is velocity and d2z by dt square is acceleration. So mass into acceleration is the force due to inertia of that system. So mass into acceleration, that will be the applied force due to air pressure that results, minus the viscous force that comes from the gland friction here, minus the spring force. So we get m d2z by dt square equal to PA, the force due to air pressure, minus beta dz by dt, the force due to the gland, minus kzt. So the force due to gland we have modeled similar to a dash pot. It opposes the velocity. Okay. Now we also realize that the flow through the valve is dependent on upstream pressure and downstream pressure, P1 minus P2, the differential pressure across the valve, this delta P, which is represented by P1 minus P2. Of course, with its square root. So Q is proportional to square root of P1 minus P2, and this thing CV times Z is called as the valve coefficient. In this case, the valve is moving, so corresponding to each position there is a corresponding coefficient which is represented as CV times Z. So the flow through the valve is the proportionality constant, which is of course dependent on the valve position, into the square root of differential pressure across the valve. This is the information available from the valve handbooks or from the process control literature. At equilibrium, we assume that the position is Z naught and the corresponding coefficient is denoted by CVZ naught. So equilibrium flow is CVZ naught into square root of P1 minus P2. Of course, P1 must be greater than P2, otherwise there will not be any forward flow. So that has to be ensured by the process design. And both P1 and P2 are constant at their respective values, P1 and P2. So any changes in Q are due to changes in the valve position, and that valve position means that the coefficient of flow through the valve, that's CVZ, that changes with the position. Now this CVZ, its variation with position is dependent upon the valve design. So generally we have three types of valve. One is called as equal percentage valve, other is called as the linear valve, and other is called as the quick opening valve. So in these three valves, with the valve opening the position Z, this CVZ varies either like this or like this or like this. So this is the linear valve, this is equal percentage valve, and this is the quick opening valve. There can be other kind of characteristics, but these three characteristics are very common. And we are assuming this valve to be a linear valve, so that this CV with the valve position is expressed as a constant of proportionality into Z. So this Q becomes mu into ZT and CVZ into square root of P1 minus P2, which is mu into square root of P1 minus P2 ZT. Pause karo. So for the valve in which the flow coefficient, which is shown on this axis, varies linearly with the position, we will have CVZ equal to a constant of proportionality into Z. And this we substitute here to obtain Q equal to mu. Of course, this P1 minus P2 square root we have pulled on the left and Z we have kept on the right. So this mu root P1 minus P2, because this differential pressure across the valve is also treated as constant in this case. So we have plugged into another constant of proportionality alpha. So Q is alpha into Z. This is the outflow through the valve, which comes out to be proportional to the position of the valve. So we obtained the two equations governing the valve. One equation was this, where the valve stem, gland and the spring, they were represented as a mass spring dashpot system, on which the force working was the force on the diaphragm due to the applied control pressure P. So we had this equation, and we had this as the output equation, Q equal to alpha into ZT. We got the equations, now we have to express them into the standard state space form. So what we do is the valve position Z and the valve speed dz by dt we identify as the two state variables. We have done it here that x1 is the valve position z, x2 is the valve speed dz by dt. So these two variables x1 are identified as the states x1 and x2. So the first equation is, because the differential of position is speed, so we have x1 dot the differential of position equal to speed dz by dt or x2. So that gives this equation. And this second equation comes from this equation, this one. It comes from this one. What we do, dz by dt is the second state. So d2z by dt is the derivative of second state. So m x2 dot equal to pa minus beta x2 minus k x1. Z we have identified as x1. We divide by m and rearrange the terms. So we get x2 dot equal to minus k by m x1 minus beta by m x2 plus a by m into p. The p is the control pressure. So we got these two equations and they are written in the matrix form like this. So we have x1 dot x2 dot. So this is the state vector x and its derivative x dot equal to x1 dot is x2 means 0 x1 plus 1 x2 and there is no input term, so 0 into u. x2 dot is minus k by m x1, so it is here minus k by m into x1 into that minus beta by m into x2, so minus beta by m comes here, and this a by m into p comes here. A by m into the applied pressure, p is treated as the input u. And output is of course alpha times the position. This is outflow. So these are the two equations, state equations and the output equation. So this is the matrix A, 2 by 2 matrix. This is the matrix B, 2 by 1 matrix. And this is the C matrix, the output matrix, 1 by 2 matrix. And these two equations represent the model of valve in the standard state space form. We have one exercise for you. So everything being the same as we did in this one, however, we assume that the spring force is proportional to square of the valve position. So instead of spring force being kz with which we modeled, we are telling that let us take spring force as kz square. So what you will require doing is, you will here this spring for kz now will become kzt square, and then I suggest that you develop the mathematical model, linearize that equation and express them into the standard state space form to obtain the model of the pneumatically operated control valve into standard state space form. With this one, we complete today's lecture. We will resume with more examples in my subsequent lecture. Thank you.